So question number 81 involved you using the partial fraction decomposition. So I have a problem here. And again, if you recall from one of my previous lessons, you never want to change the numerator, right? Your numerator value will remain the same. However, you do want to alter your denominator value, right? So we always want to factor and see how we can factor the denominator, right? If we can factor it as x plus 3 times x minus 2, well, these are two distinct linear factors. Then we can write this as a divided by x plus 3 plus b divided by x minus 2, right? And then bring this into the form of the denominator, right, while multiplying a and b by whatever those variables need to be multiplied by, right? So same concept here, but the first thing is always factor the denominator, right? So the first step would be to factor the denominator. But here when we're looking at this case, right, clearly we can group anything, right? We can factor x cubed and 7x squared and then factor 11x minus 5, right? There's no grouping that works here. So what I will do here is, because I know that I cannot actually see anything that is being factored, I would use the rational zero theorem. The rational zero theorem. And if you recall, this is a theorem that states you have possible factors, right? If you do p over q, you get the list of all possible factors. And so when I'm saying p over q, really what this means is that p includes all the factors of your constant, right? Which is this. And q here is all the factors of the leading coefficient, right? Is this x cubed over here. So in this case that would be 1. So when we're looking at the list of possible factors for a constant, that's plus minus 5 and plus minus 1. And the possible factors for a leading coefficient, well, that's plus minus 1, right? So overall, the list of possible zeros, right, that we may have is plus minus 5, right? Or plus minus 1. All I did is I divided plus minus 5 by this, 1 over here, and then plus minus 1 by this. So you get these are your four possible zeros, right? That may work for this specific polynomial here, right? So one of them could be your zeros. Again, we do not know which one is, but these could be. And obviously we can then use synthetic division to actually see if if 5 is a solution or if negative 5 is a solution. But what happens is, for the first time, what I prefer doing is I would just take any value, because we only have 4 values that we're looking at, and plug that into this polynomial. So if we plug 1 in or 5 in, right, and we get a remainder of 0, well, then that's a good sign, because if we get a remainder of 0, then we know that, for instance, if we plug 5 into this polynomial and we get 0, then we know that x minus 5 is a factor of this over here. Knowing that this is a factor, then we could possibly divide this by x minus 5, right, to seek the to seek our quotient, really, which will have the x squared, and then we can see if that further factors out or not, right? That would be using synthetic division. That's the remainder theorem, right? If you're dividing something by x minus r, right, and then you plug the r into this and you get 0, well, then x minus r is a factor of this polynomial. So that's what I do, and because I know there are only 4 possible zeros here, I just ended up taking 5, right? I ended up taking 5 here, and so if we look at 5, right, we can use the calculator, right? So we have 5 cubed minus 7, and then we have 5 squared plus 11 times 5 minus 5, right? And so I'm just going to put that in the calculator. So obviously we know this is 125, right? And that's 25 times 7, right? That's 175. And then we have plus 55, and then minus 5, right? So this over here is 50, plus 125 is 175, minus 175 is 0. So clearly we see that when we're plugging 5 in, right? When we're plugging 5 in, this is giving us 0. Well, if that is true, then x minus r, or x minus 5, right, is a factor of this denominator here, right? It has to be a factor then, right? Because when you plug 5 in, you know 5 is a 0 of this polynomial. Therefore, x minus 5 is a factor. And if you recall from synthetic division, when you're dividing on this side, so if I have something like this, right, and when I'm dividing, the variable or the expression I place here is x minus r, right? It's always x minus r. So in this case, we know that because it's x minus r, in this case r would be 5, right? We are placing r here, right, along this column. So we know that that will be 5 in this case because x minus r and then x minus 5 is, so we know x minus 5 is a factor of this polynomial. Well, if you're looking at x minus 5 and x minus r, you know that r must be positive 5. Now, well, if this was x plus 5, right, then you would have negative 5 over here, right? So really what you're saying is that you're putting the 0 here. You knew that your 0 is 5, right? And then you're just putting that 5 over here, right? So now you do that, and obviously you're dividing x cubed minus 7x squared plus 11x minus 5 by x minus 5. So you want to do the concept of coefficients. So here we put 1, negative 7, 11, and negative 5, right? And then we carry down this 1, times that by 5, you get 5, and then we add these, right? So we get negative 2, times that by 5, we get negative 10, we get 1 here, right? Times that by 5, get 5, add those two, we get 0. So obviously we knew we were going to get a remainder of 0 because x minus 5 is a factor of this polynomial here, right? So now this is a good thing because we know that our denominator is x minus 5 times x squared minus 2x plus 1. And I got that from this, right? These are the coefficients. You know your degree must be 2, therefore it's x squared minus 2x plus 1, right? These numbers over here represent the coefficients of your expression of your quadratic function. So x squared minus 2x plus 1, right? And so you have your denominator. Now, can you further factor this out? And if you look at this, yes, you can. This becomes x minus 1 squared. So you have x minus 5 times x minus 1 squared, right, in the denominator. That's a good sign now because you have that concept of repeated linear factors, right? For again, there is a rule for that when you're doing partial fraction decomposition, and this is your distinct linear factor. But you were able to successfully factor this into those linear factors. So now we're done with the factoring step here, right? So now what I would do is I obviously, so let me just write this again. So I have negative 2x squared plus 19x minus 13 divided by x minus 5 times x minus 1 squared. Well, now what I'm saying is that a divided by x minus 5 plus b divided by x minus 1 plus c divided by x minus 1 squared, right? This must be giving me this expression over here, right? So now what I do is, again, I want that denominator, I want a common denominator here, which is effectively this, x cubed minus 7x squared plus 11x minus 5. And so what I do, how would I do that? Well, I have x minus 1 squared times x minus 5. This is what I have here, right? So I can just erase this here quickly. So well, if you want, I could write that over here just quickly. So I have a divided by x minus 5 plus b divided by x minus 1 plus c divided by x minus 1 squared, right? And so we know that this must equal this expression over here. Well, we want to find the common denominator, which we have here. And so now we're going to be multiplying a by x minus 1 squared plus b by x minus 1 times x minus 5, right? And then plus c times x minus 5. So we are multiplying the numerator, right? And we have this over here, Well, x minus 1 squared times x minus 5, that is this, right? That is the factored form of x cubed minus 7x squared plus 11x minus 5. So this denominator over here and this denominator over here are obviously equal. Well, therefore we can say that, oh, this numerator, right, must be equal to negative 2x squared plus 19x minus 13, right? Because that's the numerator, right? So now we have it. Now we can say that let x equal 1. So if we let x equal 1, well then obviously this goes away, and then we are left with negative 4c. And then we can plug 1 into this expression. So if we do that, 1 squared is 1, negative 2 plus 19, 17 minus 13, that's 4. So we know that c is equal to negative 1. Right? Now, similarly, we can say that let x is equal to 5, right? Because then in this case, c would go away, b would go away, and we would be just left with a's, right? So if we say that let x is equal to 5, right, then we would have 4a, right? Or no, sorry, my bad. We have a square here as well. So we have, if we say that let x is equal to 5, then we would have 4 square a, so that would be 16a, right? And then we can plug 5 into this expression, and if you do that in your calculator, you should get 32. So you know that a is equal to 2. So c is equal to negative 1 and a is equal to 2. And for your final one, you can say that, so I'll just erase this quickly, or I have space here. So I could say let x is equal to 0. And so when I say let x is equal to 0, well, you can look at this and you know that, well, you have this. So you're really plugging the value of 0 into this expression over here, right? So you get negative 1 squared a, right? And you know that your a value is just 2, right? So we know that's 2, so we have negative 1 squared, right? That's 1a. So that gives us 2. Plus, well, we know x is equal to 0, so we have negative b, right? Negative b. So we can say negative b here. And then we have, well, we're looking at negative 5 here, right? So we have negative 5. And then we have plus 5 is equal to negative 13, right? And if we further solve this, we're evaluating this, right? So we should get 7 plus 5b is equal to negative 13, right? So 5b is equal to negative 20, therefore b must equal negative 4. So your b must equal to negative 4, right? So we know that the value of b must equal to negative 4. So when I said let x is equal to 0, because I knew the values of a as well as c, right? You know their values, and you know and you said that let x is equal to 0. I pick x is equal to 0 because it's easier, because obviously all of this goes away, and you're just left with negative 13. Right? And then you're really just saying negative 5c, you know the value of c being negative 1, so you have plus 5 over here, and you do the same thing here. You have negative 5 times negative 1, which is positive 5 times b, right? Which is what you're evaluating, right? So you were evaluating that 5b, and then obviously with your a, you had a is equal to 2, right? That's what you got. So 1 squared, that would just be a, which you're looking at, which you already know was 2. And so really you know the values of a and c, and so knowing their values and then really taking any value for x, I took 0 because it's easier. You can derive the value of b then, and b is equal to negative 4. So now I can erase all this mess over here, and your final answer, right? Your final answer using partial fraction decomposition would be 2 divided by x minus 5 minus 4 divided by x minus 1 minus 1 divided by x minus 1 squared. So this is your value here, and again, all what I did was the values of a, right? A was equal to 2, right? And then b was equal to -4, and c was -1. A is equal to 2 here, b is equal to -4 here, and then c is equal to -1 here. And so really, what the original expression that we had, I'm just taking the values of a, b, c, and placing it into these three fractions, right? We have split this into three distinct fractions here. That is what partial fraction decomposition means. So our answer here is 2 divided by x minus 5 minus 4 divided by x minus 1 minus 1 divided by x minus 1 squared. So thanks for watching.